Hello everyone. Today we'll be solving an interesting problem on Leetcode. So, what is this problem called? Problem called find in mountain array. So, first let's look at the problem statement. So, you will be given a mountain array. So, what is this mountain array means? First, in the left hand side, the elements will be in increasing order. Then there will be a peak element. Then after this peak element, the elements will be in decreasing order. This is basically called mountain array. Then in this mountain array, you have to return the minimum index such that error of dot get index equals to target. Means there will be a target element given. You have to return the index that is equals to the target element, but that will be the minimum index. Means if there exist two target element. So let's look at the example first. So there is an array and elements are given like 1 2 3 4 5 3 1, and the target is 3. Now if you look at the array, there are two position where the 3 is exist. The first position is position 2 and the second position is position 5. Now if there are two such position, you have to return the first index, first occurrence of this element. So the output will be 2. And why this is a mountain array? Because this part of this array is in increasing order and this part of this array is in decreasing order, right? Now let's look at our next example, second example. So this is also a mountain given. So this is our peak element and target is given 3. Now if you look at this array, there is no such element that is equals to 3. That's why you have to return -1. Means you have to search for the element first, then if you couldn't find that, you have to return -1. Then what is the next thing? You can't access the mountain array directly. Means you can't access the element using this ARR of 0. Means using square basis, that you can't access. Like let's say I want to access like ARR of, let's say I want to access at index 2. That we can't do that. For that, there is interface given. To access element, you have to use this get method, and to calculate the length, you have to use this length method, right? Then there are more than 100 calls of dot get method is not allowed. Means, so if you look at this constraint, what is the size of the array given? The possible size could be at 10 to the power 4, means 10,000, right? But if you apply linear search for searching, let's say I want to search for this 3 by linear search. First I have to go to this index, then this index, then this index, up to the last, right? Then what will be the time complexity for this algorithm? Will be big of n. That would be not possible because 10,004 iteration is not possible here. That is limited to 100 calls. Then what will be the solution? The solution could be linear search. We have to apply linear search, right? Now let's see how we can solve this problem. Let's say there is a array given, mountain array, and let's say elements are like 1 2 3 4 5 6, not 6, actually it is 3 2 1, right? So this part of the array is in increasing order and this part of this array is in decreasing order. So, and a target element is given, target equals to 3. Now we have to find this target in this array. We can't apply linear search here. Then what is the solution? So the solution could be, comes to our mind, is binary search, right? But here is a problem here. We can apply binary search for sorted array. Means if the array is in increasing order or is in decreasing order, then only we can apply binary search. But here you can see the some part of the array is in increasing order and some part of the array is in decreasing order. Now how we can solve this problem? Can you do that using binary search? Let's think about it. Yes, we can do, right? We can't apply binary search for the whole array from 0 to n minus 1. But what we could do, we could apply binary search for this part, and also apply binary search for this part. That we can do, right? That we can do, because this part is sorted and this part is also sorted. We can apply binary search for left or right. Now, first read the question. If we find the element at the left side, means we have to find the element at the first occurrence, then we can immediately return the index. Means first, definitely first we have to search at left hand side, because we have to find the first occurrence. And if we couldn't find in this part, then only we can search for this part. So first we have to search in this part, then we can search for this part. But here is the problem is to find this element. What is this element called? This is called peak element. This is called peak element. So what are the steps in this problem? First, we have to find this peak element. Then if we could find the peak element, then left part is sorted in ascending order and right part is sorted in descending order. Then we can first apply binary search for the left side, and if we could find the target element, that is okay. Then but if we couldn't find in the left hand side, then we can go for binary search for the right hand side. And in the right hand side, if we couldn't find the element, then at last we have to return -1. That is the problem. So the first step, in the first step we have to find the index of this peak, right? Then in the second step, next step, we can apply binary search for 0 to left side, means from 0 to this peak, right? Peak index up to peak index. Then third step will be we have to apply binary search. If in this part we couldn't find the element, then we can go for the third. Then we can apply this binary search for this. I of p is already given, so we can go from I plus p plus 1 to last, means n-1. So that are the step. And at the last, if we couldn't find in this part also, then we can return -1. So this is the problem. Now let's look at how we can find the peak element first. Let's see. So this is the array 1 2 3 4 5 6. Sorry, not 6. This will be 3 2 1, right? Now what is the peak element here? This is 5, right? This is 5. Now observe carefully the element previous to this 5 and the element next to this peak element are less than this peak element, right? Means you can write like ARR of peak is obviously greater than ARR of peak plus 1, also greater than of ARR of peak -1, right? But we can ignore this part. We can simply ignore this part and we can do this part. How? Let's see. First, let's forget about the binary search. First, let's see how we can apply in linear search. First, what we have to do? We have to first will be in this index and then we can compare this, right? What we have to check? If this index is greater than this index, means current index is greater than the next index, then we can say this could be our peak index, right? Now tell me, is this applicable for here? No, right? Then if it is not, then we can search for this element, then this element, then this element. Then when we are at this element, we can say that when we are at this element, we can say that this element means error of peak is greater than error of peak plus 1. Means this could be our peak index. That we can search by in applying linear search, right? But how could we apply in binary search? For binary search, this is also like similar. Let's see how you could do that. To apply binary search, first, what is the first thing? First, we have to take 2 pointers. One is for low, one is for high, right? Then what is the next step? We have to find the mid. Let's say this is our mid. Then we'll check if error of mid is less than error of mid plus 1, means this element is greater than this element. Let's say we are comparing this with this. This is m plus 1, right? So we are comparing this element with this element. Now if we find this element is smaller, this is smaller, and this is larger than this, then tell me between this what could be the peak element between this, whichever is greater, right? That could be our answer. I'm not saying that this is the only answer. I am saying that this could be the answer. Then whatever element at the left, can we consider? Should we consider? No, right? Because this is greater than this. This means this also greater than this, means all the elements is smaller than this element. Then what we could do, we could move this pointer, to this. Means we can decrease the space, means we can move this pointer to this. Let's remove this. So we can remove this. So then we can forgot this part. We can forgot this part. Then we can apply binary search for this part only. From here to here. So our low will be here and our high will be here. The next step, what is the next step? We have to find the mid element. Then what will be the mid here? It will be here, right? This will be our mid. Then same thing we can apply. We'll check if our error of m is less than error of m or not. Means we'll compare this with this, m plus 1. Now tell me, this is our error of m 3, this is our error of m plus 1, and this part of the array is sorted in descending order, right? So let's remove this out. So remove all the things. Okay, now let's remove this also. Okay, now let's think about this part. This is 2 is less than this. Now tell me, this part is sorted. Now tell me what could be the possible answer between them, between 3 and 2. Whichever is larger, 3 is larger, greater than 2, right? Then we can say that 3 could be our possible answer. I'm not telling that 3 is the answer. I'm saying that 3 could be our possible answer. Then what we could do? We will be moving this high. We'll be moving this high to whatever the larger element, whatever the greater element between them. Means previously what we have do, uh, previously what we have done, if error of m is greater than error of m plus 1, then we just shift this l to m plus 1, because this is greater, else in the else condition, if it is false, means if error of m is greater than error of m plus 1, then what will be the answer? Then we can shift this high to m, because between m and m plus 1, m is greater, right? Then we can shift this high to m. So these are basically two condition, right? Then what will be the next step? So this part is done, this part is done. Okay, now low is this, high is this. Then what will be the mid? Mid will be here. This will be our mid, right? Then again we'll check mid with mid plus 1. Tell me what is greater, mid or mid plus 1? This is greater, right? Then we'll be moving this high. We'll be moving this high to this. Moving this high here. Also remove the same. Now, what will be the mid? Mid will be here. Mid will be here. Now high is here, low is here, mid is also here. Now tell me, can we compare with the next element? Because we have already dropped this part, we have already this deep dropped this part. Then whom do we compare with this element? Because high is also same, low is also the same element, right? Then mid is also same element. That is our base condition. Means if high is equals to low, then we can say that this is our peak element. Means if there are only one element is pending, one element is there, that is basically high equals to low. Okay, this means one element is pending, one element is pending. Then we can say this is our peak element. Then we can return low or high, whatever we can return, that we can return. So what is the condition? We'll be repeating this process, we'll be repeating this process until this low will be less than high. When this low is equals to high, when this low is equals to high, we'll not execute this loop, we'll just return low or high, whatever we can return. That are basically same, right? I hope now you have understood. Now let's go to our code. Now let's create a function. First, let's take a variable to calculate the length of the function. So what will be the length? We have to write a mountain ARR, then dot length, and this will be our length. And then what are you gonna do? We're gonna what is the first step? First step is to we have to define a function to calculate the peak elements index, right? So let's say def, name it as find peak. Okay, then it will take self, then it will take array and low and high. Then what we're gonna do? First, we'll run a while loop. Then we'll check what is the condition. We're gonna run this loop while L less than H. Then we'll check if error dot get, because we have to use this get method. Error of get aim. Okay, we have to find the aim first. First aim, take a variable aim equals to L plus H minus L float divided by 2. That is our aim. Then we can check if our array at aim is less than error of dot get aim plus 1. So aim plus 1 is greater. Then we can simply say that our left will be in plus 1. In else what will gonna happen? So will be change this high to aim, right? Then after this while loop will be return whatever we could return. We can return L or we can return H. So this is our function. So let's find the peak element first. So let's name it as peak ELA index equals to, we have to call this function self dot find peak. Then we have to pass this mountain error. Then what do you have to pass? First we have to pass the low. So initially low will be 0, and what will be the high? High will be n minus 1, because we have to run from start to end, right, to execute this function. Now we are getting this index, right, peak element index. Now what is the next step? What is the next step? The next step is to apply binary search between 0 to index of p. Means whatever index we have get will be apply binary search for this part. Now let's see how we can apply binary search. Let's see, this is our array. So 1 2 3 4 5 6 7 right? Okay, so this is our array. And let's say, to apply binary search, first we have to consider this low pointer, then high pointer, right? Then what is the next step? We have to find the mid pointer. Let's say this is our mid, and obviously a target element is be given. Target is, let's say, 2. Okay, let's say 2, or forget about this target. Let's remove this target. Okay, now how to apply binary search? Let's say this is our target element. Let's say this is our target element. This is our target element. Okay, now let's say our mid is in the, our mid is here, our mid is here. Now what we can compare? Now we can compare that if error of m is equals to target element, if our element is equals to target, then we can directly return this m. Then we can directly return this m, means this element is our target element, right? This index is our target elements index. But that is the first case, right? That is the first condition. Now in the second condition, let's say our mid element, let's say this. Now error of mid is less than target, right? Now in that case, what will be the space? What will be the remaining space? What part we can drop? We can drop this part, because this is sorted part, right? This whole array is sorted. Now if the target is greater than this element, then we are definite that we couldn't find that element in this part. Then what we could do, we could shift this left position to this m plus 1. Why m plus 1? Why not m? Because this is already not the target. Then why we can compare this? Right, we can only compare with m plus 1, right? Then what will be our new space, a new searching space? This will be, okay, this will, this m plus 1 will be basically low. Okay, this will be low and this will be high. Then we can do the same thing, will be calculating the mid. Calculating the mid, let's say we are at this position. Now what we can say, this error of m is greater than a target element, right? This error of m is greater than target element. Then what we can do, that we can ignore this space, because if target is less than this middle element, then we are sure that in that part we couldn't find the target, means we can, then we can remove this part, and we can shift this h to here. That will be our new high, right? Then what is the next step? So then we can see that our low and high are same. Then what will be the mid value? Mid value will be this element, because if low and high are same, then the mid will be also same, the low, right? Then at m, at mid value, we are getting this target, right? So this is the 3 step. If we could find the target at this index, then we can do this. We can directly return this m. Or if we could find that error of m is less than target, then we can increase this space. We can do this, like our low will be m plus 1, and error of m is greater than target, then we can see that high will be m minus 1, right? This is 3 step. And this operation, this 3 operation will do up until we couldn't find this target element. Then what will be the condition? So we are also considering this when l equals to h. That is also considerable, right? So that's why we'll run this until this l less than or equals to I. So that is the condition. And at last, if we couldn't find the element, let's say we are at this element and this target is any target is else, like target is 20, and that is not present in this element. So let's say target equals to 20, and this target is not here. Then what we can do, we can return -1. Means we can't shift this anymore, means we can't cross this L. So in the next step, what we gonna do, it will be cross the high value. Means low will be in the left side, right side, and high will be in the left side. That will not consider. So this is our condition. We'll do this operation until left less than equals to high. Right? So let's see how we can. And this is for the increasing order, right? So this is for this increasing sequence, right? So let's write a function for this. Let's say def. There are three steps for this problem. Let's name it as binary search for order. Okay. So what it will take self, then ARR, then L, H, then what are you gonna do? First, we'll run a while loop. While what is the condition? Condition is L less than equals to H. Then we'll find the mid M equals to, that is basically same, plus H minus L divided by 2. Then we'll check if we find that error dot get M is equals to target. Yes, this target. Okay, we'll take the target here also. Target. Okay, if we find this target here, then what we can return? We can return. This is typical binary search. We can return this M. Then elif error dot get. What is the next condition? So if error of M is less than target, right? M is less than target means we are at our aim is at left side. Then what we can write, we can shift this L to M plus 1, and else what we can do, we can move this high to M minus 1, right? And at last, if we couldn't find that, we can return -1, right? So this is for increasing order part. Now similarly for decreasing part, it will be reversed. Let's say let's say 6, 5, 4, 3, 2, 1. Okay. Now initially first we'll be taking this as low, this as high, right? This is high. Now we'll calculate the mid here. First mid, let's say mid is here. Now let's say target is 5. Let's say target is 5. Let's say this is our target. This is our target. Okay. Now we are at this position, means error of mid is less than target, right? Error of M is less than target. Now if it is the condition, then target is greater than M, target is greater than them, then we can ignore this part. We can shift this high, we can shift this high to, we can shift this high to M plus 1 here. That will be our new high, right? So then what are we gonna do, we're gonna shift this high to M minus 1, right? Then what is the next step? Next step will be calculating mid again. So L is here, M is here. Now let's say mid is here. Now error of M is greater than target, right? greater than target. Then what we have to do? We have to move this left position. We have to move this left position to what? M plus 1, right? So this is the condition. And when we find this error of m equals to target, then we can directly return this m. So let's write it. So we'll be creating similar function. Let's copy this and paste it here. And this will be for decreasing order, right? It will take same thing, and it will also compare first. If it is equal, then it can return m. And if this m, error of m, is less than target, then what we can do? We can move this high to m minus 1, and else we can move this l to m plus 1, right? So these are the three steps, three function. First, we have to find the peak element. Then we can apply binary search for the left part. Then we can apply binary search for the right part. Let's see. Okay, we have find the index. First, we have to find the first occurrence of the binary search part. First, let's create a variable called, let's say, increasing part index, and it will be uh, it will return when we apply this binary search for the left part. So for this, we have to call this function binary search for increasing order part. Then we have to pass the mountain array, sorry, error. Then after this, we have to pass the low. So low will be 0, right? And high will be this peak element, index. And target will be target, what we have get, right? Then what we have to check? We have to check if we find this increment index. If this increment index, uh, it could return -1, right? So we have to ignore. If it is not equals to -1, then we can directly return this increment index, right? Otherwise, we have to go for binary search for the right part. So let's name it as decreasing order index. You can name it as you like, self dot. So you copy this function and paste it here. Then it will be mountain array. Then what will be the limit? Let's say peak element index plus 1 to target, right? And then at last will be return this decrement index. If we couldn't find the increment index, we can return this decrement index. Let's see. Let's run this code. Okay. Array target element, peak element. Okay. We have to give the high pointer. It will be nothing but n minus 1. Now let's run this out. Okay. The first test case is passed and second is also passed. Let's try to submit this code and let's see. Okay. This has accepted, and you can see this is 41 millisecond. Yes. So this is passed. And let's see the submissions. Yeah. So this is all about this problem. And if you could find any difficulty, you can write in the comment. And also, if you prepare for any interview, coding interview, we can follow this playlist also. So that's it for today's lecture. See you in the next video. Thank you.